Final lesson of the final packet. And now the real work begins. Everything else is a foundation for the house. Now we got to build that house. And that's the prep work involved, all 9 units, that you can bring it together when you have to. So you're never going to be told, hey, this is this type of question. You're going to have to recognize and be able to handle it. And that comes from practicing. So we already talked about this, that integration is more challenging than derivatives. Derivatives is just kind of straightforward, follow the formula. Sometimes integration's that way, but sometimes it's not. Sometimes you got to really manipulate, right, what you see to make it work. So look at example number 1. It says adding and subtracting terms in the numerator or multiplying by both the numerator and denominator by a common factor may make integration possible. So I want you to look at number 1. What would, if you took the derivative of the denominator, what would it be? What's in the numerator? So let's make it 2x plus 2, but then what do I need right beside it? Do you see how they're the same? I added 2 and subtracted 2, so I didn't change the value of it. These are the fun parts for people like puzzles, right? To be able to, you know, who wants the exact same puzzle every time? The fun part of a puzzle is that you don't know the answer. You got to work with it and think. All right, so can you see I added 2? Why did I add 2 again? So that the derivative of the denominator, right, would match. So that actually, because you know this so well, is ln, right? But what did we have to do because I added 2? So we're going to separate this into 2 integration problems. And there's a dx there. So one integration problem is going to be 2x plus 2 over x squared plus 2x plus 1. There's 1. And the other is going to be a little bit of algebra, right? So that entire denominator belongs to each term in the numerator. So I brought the first 2 together, but the last one I separated it as its own fraction. You ready? So what did I say would happen if you integrate the first one? Ln, absolute value of plus 2x plus 1. Done. Yay, right? So I integrated the first one, no problem. And how did I make it a ln situation? Is I added or subtracted a constant, right, to make it work. How about the second one? How would you integrate that? So now just look at the second part. So I want you to look, and obviously the derivative of the denominator doesn't help us, right? Does anyone have any spider sense that when they see the denominator, they know it can be factored? That could be a direction to go? So x squared plus 2x plus 1 is factorable. It's a perfect square. Like that should be a little bit spider sense there that goes off. What 2 numbers multiply to 1 and add to 2? What is that? Help. No? What 2 numbers multiply to 1 and add to 2? What is that factored? X plus 1 squared, right? 1 times 1 is 1, and 1 plus 1 is 2. X plus 1 times x plus 1 is x plus 1 squared. How does this algebra help me get my answer? What's the derivative of x plus 1? 1. What do I have up there? Is that easily changed? Where I could put the 2 in front and then just make that a 1? Now how would you integrate that? X plus 1 squared, how would I write that without a fraction? What would it look like? X plus 1 to the negative 2. And then you would do the anti-power rule, which is what? So the anti-power rule, I'd add 1, and negative 2 plus 1 is negative 1, and then I would divide by -1, and don't forget the candy. Recognize that the negative and the negative, you could definitely make that +2, and then that. When you look back, it's not that complicated, right? But no one told you the direction to go to integrate that way. You're going to have to see the puzzle there. And can you manipulate it algebraically to complete the puzzle? Practice is what helps. 2. What do you think I look at right away? I look at the denominator and go, what's the derivative of the denominator? And do I see it in the numerator? That's my first instinct. If I made this to the exponent 1, it would be a ln, right? The other thing I look at, is it in the form of arctangent, where it's being squared and that would help? No. Now, the derivative of this is e to the x. What do I need in the numerator? E to the x. So guess what I'm going to do? Feels like you're just making up the rules as you go, right? You're going to add e to the x, because that's what I need. But if you add it, you also need to subtract it. Now, guess what we're going to do? Separate them, right? So what are we going to separate? So first, I'm going to separate the and then the second one.
Is the x plus 1 considered a monomial?
Here, let me write that again. So, yeah, it's not 1 minus, right? It's 1, right? 1 plus e to the x. And then the second one has the subtract sign. So can you see how I separated them?
So, with the first one?
And be what?
Add 1.
Can you see how they match exactly? So again, the idea of crossing out is really dividing out. They divide to what number? 1. Oh, now we're ready. What's the integration of 1? X. What's the derivative of e to the x? Is it there now? So how do I integrate that then? No, how do I integrate it? Right? The rule for ln, right, is 1 over. And the hook is in the numerator. So this is x. This now is the rule for ln, and you follow the rule for ln. You look at the denominator. The derivative of the denominator is in the numerator. It's ready to go. The hook is there. It's ln of whatever's in the denominator. If you took the derivative of this, what would it be? 1 over e to the x plus 1 times the hook, which is e to the x. You can see how it matches. Number 3. A trig substitution, or using a trig identity, may be necessary for some problems. The common trig substitutions are for what? tangent squared, cotangent squared, and the like, where you use these, right? Like taking sine squared plus cosine squared equals 1 and changing it in terms of tangent squared, secant squared, or cotangent squared, cosecant squared. Can you integrate this? So when I see tangent squared or cotangent squared, what can I put in its place? And why do we want to do that? Because secant squared is a rule, correct? Cosecant squared is a rule. You did that right? Beginning of class. But tangent squared and cotangent squared is no rule. So what would that look like if I did that substitution? So tangent squared is what? Secant squared. Now instead of x, what do they have in there? So just put in 2x. And cotangent squared is up here, right? What is it? Cosecant squared. Instead of x, again, I put in 3x minus 1. Now what are we going to do? Each one, right? So when you have adding or subtracting, what can you do? Just each one separately, right? What's the integration rule for secant squared? Now, is there a hook involved? What's the hook? So how do I undo the hook? Yes? You see how we did? The better we get, there's no like brownie points for like going to extra, to show everything in there. It's okay to be able to go from here to here. That's full credit. Negative 1 is what? Negative x. How about cosecant squared? What's the rule? Negative what? Cotangent? Is that right? And what was the hook? 3. And how do I undo the hook? Can you see how we're doing that? And we're getting better and quicker and more efficient at it. And negative 1 again is, and then don't forget the candy. There's no brownie points for collecting like terms there. All right, let's look at another example. Definite integrals means that we have bounds. Involving absolute value expressions can often be evaluated by using the idea of signed area or symmetry. Often when you see absolute value in something, it's really good to be able to graph it, to be able to see it graphically rather than try to do it algebraically. However, more complicated integrals involving absolute value may require you to split the integral and do it that way. So it says set up integrals which do not contain the absolute values that should be used to integrate x squared minus x minus 6. So can you see the graph that it's a parabola and you can see it here? We're going to set up integrals. We can't do it in one chunk. We have to separate it into 3 chunks. So let's go back to understand this. Integration graphically is the area under the curve with the x-axis. So if I'm going from negative 3 to positive 5, see this area right here? That's integration. How about the next group? What's the area? And then what's the next area? Now, what do you recognize about this area if it's absolute value?
Positive.
It's positive, right? So that area actually is up here. Why does that matter? Because we need to take that area and make it what? Positive, right? That's negative area, and up here is positive area. So first, we're going to integrate from negative 3 to what number? And then we're going to integrate from where to where? Negative 2 to what number? 3. Now, if I just integrated that from negative 2 to 3, would the answer be positive or negative? How can I change it to a positive answer? See what I did? Why did I subtract that integral? Because the negative and the negative then will make it a positive area. And then what's the last part we would integrate? You'd be adding because it's positive, and we're integrating from where to where? 3 to, that's a 5, right? I'm not making you do this, but if you had to, could you do the anti-power rule, and then you'll have 3 different scenarios, and then you'd combine those answers together with the absolute value.
Oh, so
Just the setup. Turn the page. All right. There are many techniques for integration. Remember I talked about you could go in Barnes & Noble and buy a book, right? It could be like 200 pages long. So when you feel like you can't sleep at night, right? Take out the old integration book, right, of integration rules. You could do your doctorate on a new integration rule. This course deals with only the most common of them. When integrating, explore options until you find the one that works. I often think that. Take a path, and when the path fails, you go back to the beginning and try another. It's okay, right? And that's often a way to be able to like cancel out bad methods and find the one that would actually work. So practice fitting integrands into basic integration formulas that you've already memorized or will memorize. Oh, you've already memorized them.
sure.
All right, look at this one.
Let's go with that.
How can I fit this in to integrate? You know one thing I notice? Look at the derivative and the hook, right? When I go sine e to the negative 3x, guess what this is really on the bottom? E to the negative 3x, right, if I didn't write it in the denominator? So if I said, hey, what's the derivative of e to the negative 3x? You would say e to the negative 3x, and then of course you'd need a hook. I can manipulate any constant, right? I see that. And then what do you notice here? Well, they have the same base, right? And so that means algebraically, I don't have to write it as a fraction. If they have the same base, I just subtract the exponents. So how do you think I'm going to write this? You ready? I'm going to write down sine e to the negative 3x over e to the 3x. I'm going to write down e to the x over e to the 3x. No, we'll get there. Let's not trip over basic algebra yet. The first one. What's the derivative of e sine e to the negative 3x, right? What's inside the hook? I already told you. It's e to the, what's the rule for e for derivatives? E to the whatever. Do you see that here? What doesn't it have that it needs? It needs a negative 3, right? So how do I undo that? So there's going to be a negative 1/3 in front, right? For that hook negative 3. Now we're ready to go. The first part now is simple. What's the rule for sine? And we got it. What's the integration rule for sine? Just cosine or negative cosine?
Negative cosine.
It is, right? So it's negative cosine of what? E to the...
Integration.
When you integrate, what's the rule for sine? Negative cosine. Now, of course, the negative times the negative makes it but I don't care right now. But can you see? That's a lot simpler than it looks. Now some basic algebra. When the bases are the same, what do you do with the exponents? What's 1x subtract 3x? So that whole thing is just e to the negative 2x, is that right?
Yep.
What's the rule to integrate e? It's just what it is, right? What's the hook? How do I undo the hook? And I need a negative, right? And there it is. Now, of course, you can go negative times a negative, that's positive a third. A negative times a negative, that's positive a half. It's the algebra that gets the part that makes you trip, right? You know your calculus rules. Now we got to make sure that our algebra foundation is good. Number 6. Look at it before I just tell you the answer to the puzzle. Do you know where my eyes go to first? I look at the most complicated part of it, and I look inside it to see where the hook is. That's where my eyes are drawn to. Which looks like the most complicated part, right? Do you see that squared? And you know what I look at right away? Is what's inside it. If I need to take another piece of paper or scratch out and go, okay, what's inside it is what? Ln sine x. Guess what my brain wants to do? What's the derivative of that? If that was that, right, what's the derivative of ln sine x? How do you do that? 1 over sine x times what's the hook? What's the derivative of sine? Cosine, which is really just what? Now let's go back. What do you see? Hey, you. So what do you see? Do you see the hook right there? Cosine over sine? Come sit right here, Bella. So the hook is already there, isn't it? So how does that help me answer it? I'm off and running. What do I need to do here? Just the anti-power rule. What do I do with the anti-power rule? Add 1 and divide. Done. What? I got one more. You ready to stay for one more? Nice.
She's on the video now.
I know, that's great. She remembers from last year. I didn't do as many videos because I didn't have this until the end like that. Oh, she could help you prepare for the calc exam, I'm sure. Example 7. That means I got limited time. So remember that if integrals involve radicals, and you can't seem to fit the integrand into the basic integration form, you should try what? U-substitution. Now that's a complicated word to say this. What is the derivative of x plus 1? 1, right? Can you see how that numerator isn't helping us? If that numerator was a constant, boom, it's to the exponent negative a half, add 1, divide, done. But it doesn't fit, right? So instead, what would a U-substitution look like? What part doesn't fit? X plus, what does x equal? U minus 1. What's dx? Right? And now, how do you substitute in? So where you see an x, what are you going to put in? U minus 1 plus 2. And the denominator, x plus 1 is just u, and dx is just du. Clean this up a little. Negative 1 plus 2 is plus 1, I hope. What would you do to integrate from there? What technique did you learn today and on 9-6 that you can do with this? Separate them. So, what's going to happen? One's going to be u over root u, and the other is going to be 1 over root u. How does that simplify? U over root u. They have the same base. The exponent is 1/2. 1 take away a half is 1/2. What's 1 over root u in calculus form? Negative a half. And now we're off and running. So now it's in the form anti-power rule. What am I going to do to the 1/2? Add 1 and it is, and then divide or do the reciprocal. Do it again. Add 1, and what do you get? 1/2. Divide by 1/2, or the reciprocal. Don't forget the candy. And then what's the last step? Put u, right? What does u equal again? X plus 1. All right, that's it. Now the hard work really begins.